All right, chemistry class, we are going to continue our discussion about acids and bases. And if you got your notebook there, we need to take some notes, jot down a few things about acid-base reactions in section 14.3. So write down section 14.3, acid-base reactions. Okay? All right. Here's what we're going to talk about. We're going to talk about when an acid and a base react. What are the results? And we're going to identify different parts of that reaction, and we're going to kind of see a pattern, and we'll also talk about the strength of an acid in the reaction, the strength of the base in the reaction. Okay? So let me just look at this reaction right here, ladies and gentlemen. Here we have an acid, HF. Now, you should know how to name that. This is a binary acid. Binary means it only has two elements. One of them is always going to be hydrogen, and the other one is going to be a very reactive nonmetal, like fluorine. So this is hydrofluoric, hydro for hydrogen, fluoric for the fluorine, fluoric acid, hydrofluoric acid. When you put that in water, there's going to be a reaction, and that reaction is going to produce ions. Now, if you remember, for an acid is going to increase. When you put in water, it's going to increase the concentration of H plus, or really it's H3O plus. Because remember, we have the H plus, and when it's in water, it's added to a water molecule to make H3O plus. That is called the hydronium ion. Hydronium. Okay? That hydronium ion is one of the ions that is created when you have an acid. And then the other one here, that's your other ion that is created. Now, what I'd like you to notice is that this is a reversible reaction. It's going both directions. And if you remember, that double arrow is indicating that HF is a weak acid, meaning it will dissociate but not completely. Meaning the forward direction will happen, creating these ions of fluoride and the hydronium, but when there's too much of those ions, too many of those ions, they also can turn back into the original compounds of the fluoric acid and the water. Okay? So both directions can happen. So we have to think about this reaction in two directions, the forward direction and the reverse direction. Okay? Now let's just compare. What we want to do is we want to track something. We want to keep track of something in this reaction, and that is going to help us determine if what is in the reaction is an acid or is it a base. Now, let me just go back to something that I mentioned before, and I'll give you an example here. I said that hydrochloric acid is an acid, obviously, because it's going to break into the ions of H plus and Cl negative. Okay? It's actually a molecular compound. It's not ionic compound, but it's still going to create ions. This H right here and the Cl are going to separate into their ions. Now what really happens, if you remember, we put this into water, this H plus really is going to be added, as I mentioned up here, is added to a water molecule that's it's going in water, it's aqueous, right? And this is really going to give us H3O plus. So what we notice is that this hydrochloric acid, this HCl, donates an H to the water. This H is given to a water molecule, creating this hydronium ion right here. So we can conclude that acids donate H plus in a reaction. And that H plus, I mentioned in a previous video, that H plus is just a proton. It's a hydrogen atom with its electron, or its only electron removed, so it has just the one proton. So that is a proton. So we can say that acids are proton donors. You must write this down. Acids are proton donors. They will give up their H plus, that's a proton, H plus to the other reactant in the reaction, okay? Or maybe to the other product if you're going the opposite direction. But an acid is a proton donor. Okay, that's how two scientists, Bronsted and Lowry, defined an acid. You don't need to know really who they are, but that's how they define an acid. An acid is a proton donor. So let's look at this reaction a little bit more carefully here. Okay, here is HF, and here's H2O. A reaction occurs in the forward direction here. What now happens? Well, now we have H3O plus, and we have F negative. How did that happen? Well, the water took the H from the HF. In other words, the H plus was donated to the water. H plus, from this HF here, the H plus was donated to the water. This is your proton here. H plus is your proton. Okay? And that water, H2O, becomes H3O plus. If this H plus is donated to the water, what remains, what's left of the HF? Just the F negative. Okay? So we can figure out, if we can figure out who is donating the H plus, then we know who the acid is. The HF is giving the H plus, the proton donor, to the water. So it is the acid. It is acting as the acid in the forward direction. The water is accepting the proton. So a base is a proton acceptor or receiver. Okay, however you want to say it. It receives the proton, acids donate the proton. This water is receiving a proton from the HF, so it is acting as the base, okay, in the forward direction. Now remember, this reaction goes both directions. So let's look at the right side of this reaction, and how would these two products turn back, go the reverse direction, turn back into the reactants? Well, let's see. How is H3O plus going to turn back? I'm going the other direction now. Turn back into H2O. It has to give back the H plus, the proton, to the F negative. So the F negative now turns back into HF. So in the reverse direction, who's the proton donor? It is this hydronium. And who is the proton acceptor? It is the F negative. So you'll notice in both directions there is an acid and a base. An acid and a base. And we actually pair them up. Did you notice how I paired them? The HF is paired with the F negative. The H2O is paired with the H3O plus. Okay? And we're going to actually call those conjugate acids and bases, or a conjugate pair. Okay? So the HF and the F negative are conjugate acid-base pair. And the H2O and the H3O plus is another acid-base conjugate pair. They go together. Okay? Now, if we identify this reaction and we see that it's going both directions, one direction might be stronger than the other direction, okay? And you don't really need to figure it out. I'm actually going to give you a table that shows which acid is stronger than which, but I just want you to identify that there are some acids that are stronger than others, which means the stronger acid is going to push the reaction further in the direction it wants to go. Let me show you what I mean. If we have this reaction, and here we have an acid, it is an acid, here's the water, it is acting as a base. How do I know that? Because in order to get the products over here on the right side, this acid has to donate its H plus to the water to make the hydronium. And the HClO4 loses its H in order to make this ion right there. Okay, I think that's chlorate ion. So the HClO4 becomes just the ClO4 negative. It lost the H plus, and the water becomes the H3O plus, the hydronium. They're paired up. Now, if you are told that HClO4 is a stronger acid, by the way, I'm identifying the acids here. Here's the acid on the left side. What is going to be the acid on the other side? Well, an acid, once it donates its proton, is going to turn into the base on the other side. Notice how they're paired up. Acid on this side is going to be a base for the reverse reaction. And the base on this side, on the left side, is going to be the acid on the reverse direction. So the question is, which direction is going to be pushed with greater force? Because it may not be exactly equal. You may have more of the products than you do the reactants. How do we know? Well, we're going to compare on a table, on a chart, the acids. The stronger acid is going to push with greater force in the direction it wants to go. So since you look on the table, I'll show you in a second, we look on a table, and since HClO4 is a greater strength acid than the other acid on the other side, the hydronium, it is going to push the reaction with greater force in the forward direction. And only in the reverse direction is it going to go a little bit. So I drew a big arrow in the forward direction and a smaller arrow in the reverse direction. The stronger acid is going to push with greater strength, okay, in the direction it wants to go. So in this case, we're probably going to have more of these ions than we will of the original compound here of HClO4, okay? Here, if in this case we have an acid, it's going to donate its H. The H this time is written in the back, but this H is going to go to the water. That water is going to turn into the hydronium. And this acid is going to turn into this ion right here, okay? The acetate ion it's called. So this is acting as this compound on the left side here is your acid because it's donating the H plus. The water's acting as a base. And I know that the acid is going to turn into a base on the other side. And the base, the water, is going to turn into acid on the other side. And you can also look at the reverse reaction. The reverse reaction, in order to go from the right back to the left, this hydronium is going to have to give back the H plus to the acetate in order to get what we originally had. Okay? Now, again, talking about strength, if you identify and compare the two acids in this reaction, this is acetic acid and this is hydronium. Those are your two acids. They're identified there. And you compare them. If you see that acetic acid is weaker than the hydronium, then we know that this hydronium is going to push the reaction back this way with greater strength. I'm going to make a big arrow in this direction and not such a big arrow in the forward direction. Okay? The stronger acid is always going to push away from it, going to make that direction go with greater strength. Okay? And as promised, here's a whole list of acids, and you could just compare. So you'll notice here this arrow is showing increasing acid strength. So the strongest acids are going to be up here. These are the strongest acids. All right. The weakest acids are down here, in this area. And you'll notice then we also have the conjugate base. All right. If this is a strong acid, now over here for the conjugate bases, the strength goes the other direction. The strongest bases are going to be coming from the weakest acids. Okay? the weakest acids. And you'll see back up here, look, okay, you see how the weaker acid produces over here this base, and this base that it produced is stronger than the other base on the other side. Okay, so a weak acid turns into a base, and it's going to be stronger than the other base on the other side. Okay, so all you have to do is just refer to this chart and compare your acids, and then you'll know which one is stronger, and you'll know which direction is going to be favored, which direction is going to push with greater force. Okay, this kind of sums it up here. Point number one, you can write these in your own words or just kind of write this down and make a few annotations. The stronger the acid, the weaker the conjugate base is going to be. Okay, as mentioned from this table, strong acids produce weak conjugate bases. The strength of the acid goes up here, the strength of the base goes down. Okay? And two, the proton transfer. Remember, acids donate a proton, bases accept a proton. Favor the production of the weaker acid and weaker base. That's another way to say what I just said before. I said that the stronger acid is going to push in its direction, meaning you're going to make more of the weaker acid and weaker base. The weaker acid and weaker base are always going to be in greater concentration. Okay? The stronger acid wants to react, wants to push it in the forward direction. In this case, over here, the stronger acid and base are on the product side, so that it's going to push it back the other way. So again, what's going to be favored? The weaker acid and weaker base. So you're going to have more of these in the solution than you will of the stronger acid and stronger base. Okay? Okay, now, here is a really, really interesting thing. Water is an amazing, amazing substance. Okay? Absolutely phenomenal. One way that it is very, very interesting is that it can act as an acid or a base. I don't know if you noticed in the previous reactions, but sometimes water was an acid, sometimes it was a base. That property is called amphoteric. Okay? Any substance that can act as an acid or a base, you need to write this down. Amphoteric means it can behave as an acid or a base. Either one. Okay? So, let's look at an example here. Here, and we're specifically going to look at water. Okay? We're going to look at water. We have two different reactions. Here we have sulfuric acid reacting with water to produce hydronium and that ion. Now, let's figure out what's the acid and what's the base. How is this hydronium being created? That hydronium is being created because this water is accepting H plus from the H2SO4. So the H2SO4 is donating a proton. It is an acid. The water is accepting that proton. It is a base. Okay? Therefore, what happens? The acid is going to turn into a base on the other side. So the reverse reaction, in the reverse reaction, this is going to be your base. And the base is going to have a conjugate acid. Okay? Now, how do I know? You can also look at the reverse reaction. How does this hydronium turn back into water? It has to donate back the H plus to the HSO4 negative. So this is the acid. The acid is always the donator of the H plus, the proton. Okay? So you'll notice here water is acting as a base. Water is acting as a base. Let's come down here. Here is NH3, ammonia, and it is put into water. Let's see what happens. In this case, the water is turning into OH negative. How did it do that? Well, it lost an H. It is the H plus donor. It is the proton donor. It is giving an H plus to NH3. Look what NH3 becomes. NH4 plus. Okay? So the ammonia here is your base. It is the proton acceptor. Water is your acid. It is the proton donor. And the NH3 is turning into NH4 plus. So remember, a base in the forward direction is going to be acting as the acid in the reverse direction. And the base in the forward direction, water, is going to be acting as a base in the reverse direction. Again, look at the reverse direction. If I was to go backwards, how do I go from the product side to the reactant side? This has to donate an H plus to the OH to get back to water. Okay? So my point here, though, is in this case, water is acting as an acid. So water is an amphoteric particle. It's an amphoteric solution, substance. It is a base here. It is an acid down there. It can behave as both. Okay? In fact, maybe I'll mention this later on. Let's see here. I'll go ahead and mention it right now. Water can actually act as an acid and a base just in pure water. What? Listen, water, just pure water, does ionize to a small extent. Here's what I mean. Look, if you have water and water, water and water, to a small degree, pure water is going to ionize. What happens? Well, one water molecule will behave as an acid, and the other water molecule will behave as a base. So one water molecule will give up its proton and turn into OH negative, and the other water molecule will accept that proton and turn into the hydronium ion, H3O+. This happens to a very small extent. Not all the water molecules do that, obviously, okay? Very small degree of water molecules go through this reaction in pure water. Okay, but it's still significant. It's still a very important reaction. So in this case, this is your acid, and this one over here is your base. It's the same substance, but it's acting as an acid, and the other one has to act as a base. Okay, and on the other side, you've got your base and your acid. Okay, this is called, you must write this down, the self-ionization of water. Self-ionization of water. Okay? All right. Now, we talked a lot about the donating proton and the hydronium ion. Notice that, remember, the OH is a kind of a marker for bases. If that hydroxide ion is produced, if it's increased in a solution, then whatever's producing that or creating that is going to be your base, right? That's an indication of a base. All right? All right. Here we want to talk now about when an acid and a base combine, when they react. This is a very important topic here. So I forget what point we're on, but I'll just put a little star there. All right. So make sure this goes in your notes. When we have neutralization, and neutralization is acid plus base. Acid plus base. When you have an acid and a base and they are combined together, they are going to neutralize each other. And you always are going to produce water and a salt. And by a salt, I mean an ionic compound. Okay? A metal and a nonmetal. Now, let's look at a couple examples here. Okay? Here we have an acid, HCl. You put that into water and you're going to have the hydronium ion and the chloride ion. The HCl, the H is donated to the water. Okay? Like that. Here we have a base. When this is put into water, it ionizes, and you're going to create the Na and the hydroxide ion. Okay? So notice a base, here's your base, creates the hydroxide ion. The acid is going to create the hydronium ion. Okay? Hydronium comes from the acid, hydroxide is for the base. Now, what if we were to mix these two together? What if we were to take this acid and this base solution and put them together? If we put those together, then we're going to have all of these products in the same solution, okay? Okay, so let's look at what happens when we take the acid and the base and we mix them together. We have a acid-base reaction, okay? So here we have our acid, and remember the acid is creating the hydronium ion and this chloride ion. In this case, the HCl is creating that. The base is creating the Na sodium ion and the hydroxide ion. Okay? So let me just show you here what happens. This Na, the sodium from the base, and the chloride from the acid are going to get together to make what? Our salt, our sodium chloride. And the hydronium, actually it's the H plus from the hydronium, okay? The hydronium here, actually we can look at it this way. The hydronium and the hydroxide are going to come together to make our water. All right, the hydronium is just an H plus and water. And then when we add an OH negative, this OH and the H can come together to make our water as well. So we're getting water from the hydronium and the hydroxide. Okay, so every time an acid and a base are combined, when they are reacting together, they're always going to form some salt, an ionic compound, and water. Okay, and for us, a salt just means any ionic compound. It has the metal and the nonmetal, cation and the anion. Okay, the cation is coming from the base. The anion is coming from the acid. So that's a neutralization of an acid and a base. Okay, that you definitely need to know. Now, let's look at if we have a strong acid and a strong base. All right, here is a strong acid. This is coming from HCl, and this is coming from sodium hydroxide. So this is our strong acid, HCl, hydrochloric acid, and our strong base, sodium hydroxide. When we combine these together, the HCl, remember, is producing the H+, which we also know is the hydronium, H++ plus a water, and it's producing the chloride. The sodium hydroxide is producing your sodium and your hydroxide. When we put them all together, all four of those ions come together, what does it produce? Well, the sodium and the chloride get together to make our sodium chloride. All right? And the H plus and the water get together to make our, this actually the hydronium, see the hydronium, H3O plus and a hydroxide are going to make two waters. So we have an H2O twice. There's our two waters there, okay? So this is the hydronium and the hydroxide really are making water. The sodium and the chloride are just the spectator ions, remember that? So the basic neutralization of an acid and a base is that the hydronium from the acid is neutralizing the hydroxide here from the base and forming just water. Yes, you have a salt, the sodium and the iron chloride, the cation and the anion are dissolved in that water there as well, but the real reaction that occurs is the hydronium from the acid, the hydroxide from the base is creating water. Okay? That's the neutralization of an acid and base. So you need to know this right here, ladies and gentlemen, that neutralization of an acid and base basically means that you have the hydronium ions and the hydroxide ions are forming water molecules. Okay? All right, that actually concludes 14.3. So I hope you learned something there, and basically it is the acid and base that are neutralizing, and the acid is giving you the hydronium ion, the base is giving you the hydroxide ion. Together, that's just making water. And yes, you have a salt because of the cation and the anion are coming together to make that salt. Okay? All right, we'll see you in the next video. Keep working hard and let me know if you have any questions.